Okay, so in this video, I'm going to attempt to teach you all the calculus that you need to know for AP Mechanics. All the Calculus 1, that is. So let's get right into it because I'm going to try and do this in under 15 minutes. Here are some objectives that we would have for this section and this lesson. You can take your time and pause this and read this over, but right now I got to get moving. So let's consider an accelerating object. So to find the velocity of a position versus time graph, we know that we look for the slope of the line. And here we know that this is an accelerating object because the slope of the line is getting steeper and steeper and steeper, which means that the velocity is getting steeper and steeper and steeper. So how would we typically find the velocity here? Well, we would pick a point here, and we would pick a point here, and then we would say, all right, well, so here are 2 points, and now we have to find the slope of the line between those 2 points. So slope is rise over run. Remember that slope is equal to change in x over change in y, or rise over run. But in this case, our variables are x and t, so it would be that velocity, average velocity, is a change in x over a change in time, or x final minus x initial, all over t final minus t initial, where this would be our t initial. Point down from here is going to be our t final. And if we go over to our y-axis, in this case it's our position axis, this would be our x initial, and this would be over here somewhere, would be our x final. And we would use this point slope formula to find an average velocity between these 2 points in space. And if we wanted to get more precise as to what the exact velocity is, let's say at a different moment, let's say we wanted to know what the velocity really was right here, then we would pick 2 points that would be closer to being around where we actually want to know where the velocity was. So we would pick our initial point here and our final point here, and then this slope that connects these 2 lines would be a lot closer to what we were actually looking for, which is the instantaneous velocity at a particular point right here. So here you'll see an equation on the bottom that talks about limits, or the limit as the delta t, there actually should be a as delta t approaches 0. So as this space here, as these 2 positions in space and time get closer and closer and closer together, our slope will get more and more and more and more exact to the slope of the line at that one point on the graph. And if we were to talk about, let me clear all this. Yeah, I want to clear everything. If we were looking at one point in space and we want to know the exact point at this right there, we wouldn't be talking about an average velocity anymore. We'd be talking about an instantaneous velocity. An instantaneous velocity is a slope of what we call a tangent line. A tangent line is a straight line, which it's tough to draw here, that intersects the curve at only one point. So if I could draw a line that only just touches this curve at one point, that would be called a tangent line. And because you only have one point, you can't use this point slope formula, because a point slope formula means you've got to have 2 points to get that slope. You have to have a final and an initial. And if you only have 1 point, then you have what's called an instantaneous velocity or a tangent line, and there is a math trick for that called the derivative. So how do we find the slope at any instant, otherwise known as how do we find the tangent line or the slope of the tangent line? So this is called the power rule in calculus. I'm not going to explain where it comes from. That's for your calculus teacher. What I'm going to do is I'm going to tell you how to use it. So this is a math trick that allows us to find the instantaneous velocity on a position versus time graph. It also allows us to find the slope of a tangent line on any graph. So this will automatically give you the slope of a graph, and then it's up for you to determine what that slope represents. On a position versus time graph, that slope will represent velocity. On a velocity versus time graph, that slope will represent acceleration. But let's take a look into the math of it right now. So if we have some function y equals x to the n power, then the derivative of that function with respect to the variable x, don't think that this d is another variable. It's not. It's the derivative of y with respect to the variable x is equal to n to the x, n times x to the n minus 1 power. So what have we done here? Well, we multiplied by the exponent that's there, and then we just subtracted 1 from that exponent. So let's practice some math, and then we'll put it in terms of physics. So if we have y equals x squared, what we're going to do is we're going to first multiply by that exponent, and then we're going to subtract 1 from that exponent. So we're left with 2 times x to the 2 minus 1 power. 2 minus 1 power is 1. So we're left with just simply 2x. Easy enough, right? Why don't you pause here and see if you can finish these next 3 practice problems on your own using this same rule. When you're finished, go ahead and hit play, and I'll explain the rest. Okay, so let's take a look at this next one here on the list. So we're going to use the power rule here twice for each term in our function. So we have 3x cubed, so we multiply by our exponent. So 3 times 3 is 9. And then we take 1 away from that exponent, so it becomes x to the second power. So 9x squared. Plus, here we go, 2 times 2 is 4. Take 1 away from the exponent, x to the first power. So I'm just going to leave it as an x. Now remember that these exponents go with the variable. They aren't going with the coefficient. So here, when we do y equals x plus 5, the exponent of x is 1. So we're going to multiply by 1, and then we're going to take 1 away from the exponent, which means we have x to the 0 power. 1 times x to the 0 power is 1, because anything to the 0 power is 1. Over here, you may think that you don't have anything to deal with, but you really have 5 times 1, you could say, where 1 is x to the 0 power. This is the same thing as the number 5. 5 times x to the 0 power is the same thing as 5, because x to the 0 power is 1. So when we use our power rule, we're taking 0 times 5, which gives you plus 0. 0 times any coefficient is going to be 0. And then when we subtract 1 from the exponent, it doesn't matter because it's 0 already. We're multiplying by 0. So this answer here is 1. And we know if we were to graph this, if we were to graph x plus 5, y equals x plus 5. It's just a straight line. A straight line with a slope of 1. Y equals mx plus b. The slope is the coefficient of your first variable. 1. So our slope here is 1. And now let's take a look at this next one. So again, just like that number 5 over there, the derivative of any constant number is going to be 0. Over here, y equals 6. That's y equals 6x to the 0 power. Same thing as 6. And when you take the derivative, you get 0. This tells you that the slope of y equals 6 is 0. Hey, you already knew that. If I told you the graph y equals 6, it would look like this. It'd just be a horizontal line up at 6. And the slope of any horizontal line is 0. But this works in physics too. So here's a familiar function that we have in physics. You should all know this equation with a constant acceleration. Well, what if we did that derivative trick on this equation? So now we take the derivative of this function x. So this is a function of x. And we're going to take the derivative not with respect to x. We're going to take the derivative with respect to time. So time, the t's in here, are really what's changing, are my variables. Whereas these other things, that's just a constant, that's a constant, and then 1/2 a is also a constant. So in the last equation, or last practice, we learned that the derivative of constants, like y equals 6, the derivative of that is 0. So this constant is 0, the derivative of this is 0. And we go to the next term, this is v, a constant, times time to the first power. So we multiply by 1, and we take 1 away. So this becomes v naught, because 1 times v naught is v naught, times t now to the 0 power. But anything to the 0 power is 1, so it's v naught times t, or times 1, so it's just v naught. Plus, here our exponent is 2. We multiply by the exponent. 2 times 1/2 is 1. The a is still there, so it's basically 2 times 1/2 a. 2 times 1/2 a is 1a. Times t, and now we subtract 1 from the exponent to the first power. So 1at to the first power, that's the same thing as if I just said at. And we end up with that the derivative of position with respect to time is equal to v naught plus at, which is just the first equation in your equation sheet, otherwise known as our velocity equation. I got see here, remember that the slope here is the change in velocity over the change in velocity over the change in time. So this slope represents a acceleration, and if I were to take the derivative of that velocity function, so here I had v equals v naught plus at, where the v naught is a constant, a is a constant, v is our function, and t is our variable. If I take the derivative of that velocity with respect to time, we get the derivative of a constant, which is 0, plus at, remember t has an exponent of 1. 1 times a is a, and then take 1 away from that exponent, it becomes t to the 0, which is 1, and you end up with a. The derivative of velocity with respect to time is acceleration. And you would have just a constant number. So here we have an example of constant acceleration. But the calculus will work whether the acceleration is constant or if it is not constant. So now we do not need to rely on just the kinematics equations on our equation sheet. We can now make the equations ourselves.